Predicting the shape of molecules. So we've learned how to represent molecules using Lewis structures. So what we're going to talk about now is sort of an extension of Lewis theory. It's called Vesper theory. So Vesper, I know it should be V-E-S-P-E-R, but we're just trying to pronounce this instead of saying V-S-E-P-R, or what it stands for, valence shell electron pair repulsion theory. So Vesper theory is easier to say. It stands for valence shell electron pair repulsion. So we're looking at the valence electrons, the electrons in the valence shell, and we're looking at how pairs of those electrons repel each other, and that is the big idea behind this theory, that determines the shape of the molecule. So electron groups repel each other. So what is an electron group? Each of these things counts as one electron group. We're talking about electron groups, not electron pairs, not individual electrons. So a lone pair of electrons is an electron group. A single bond, a double bond, or a triple bond, each of those is one group. So a group could have 2 electrons or 4 electrons or 6 electrons. We won't do anything with single electrons, but a single electron would also be an electron group if it was unpaired. Okay, so we need to start by looking at Lewis structures for the molecules. So here's the Lewis structure for carbon dioxide. So the central atom, carbon, has a double bond to one oxygen and a double bond to this other oxygen. We see that the octet rule is satisfied. All 3 atoms have an octet of electrons. What we're going to do is we're going to look at that central atom and ask ourselves, how many electron groups are on the central atom? Well, a double bond is 1 electron group. There's 2 double bonds, right? So that means there's 2 electron groups. Does that make sense? So then, the way I think of this is, so here's the central atom. Sometimes it's more helpful to look at this ball and stick figure. Here's the central atom, and you have this oxygen over here and an oxygen over there, and these groups, this is a group and that's a group, they are trying to get as far away from each other as possible. Maybe this is you and that particularly nasty ex, horrible breakup, and you want to be on the other side of the planet from that person, right? You never, ever want to get anywhere close to them again. So that's what we're talking about here, just getting far, far away, repulsive. So if they can't like leave and go off to some other atom. They're still attached to the carbon, but they can get on opposite sides of the carbon so they don't have to look at each other, right? So 2 things will get on opposite sides. And so these 3 atoms will line up like this in a line, and the angle that they form here is 180 degrees. This is called a linear geometry. Any questions? Let's look at H2CO. Here is the Lewis structure for H2CO. So we have carbon in the center and 2 hydrogens bonded to it and 1 oxygen bonded to it. How many electron groups are on that central atom carbon? 3. There are 2 single bonds and 1 double bond. A double bond is 1 group of electrons. Because these 4 electrons that are being shared between the oxygen and the carbon have to stay between the oxygen and the carbon. They can't get away from each other, right? So we talk about them as 1 group. So we have 3 groups. Well, 3 things repelling each other, 3 people trying to get away from each other, they're going to spread out, and the farthest away they can get from each other is 120 degrees. If any of them moves one way or the other, up or down or anything, they're going to get closer, and that's not going to be good. A little bit like, kids in the minivan, they're going to spread out as far as possible, right? Who wants to sit by your stinky little brother? So this is called a trigonal planar geometry because it's a triangle shape and it's flat. It's in a plane. So all four of these atoms are in one plane. Both of these, the linear and the trigonal planar, they're both flat, and so they're easy to draw on paper because they are two-dimensional. Any questions? What about methane, CH4? Well, here is the Lewis structure for methane. There aren't any lone pairs on this molecule. The central atom carbon has 4 single bonds, each to a hydrogen. How many groups, electron groups, on the central atom? 4. Each single bond is 1 electron group. So now we've got 4 things trying to get away from each other. This is harder to visualize. You might say, well, why not just, do this like a square? Well, what would the angle be? What's this angle? If it's a square like this, that's going to be 90 degrees. The molecule's not limited to a two-dimensional plane. What happens is down here, and so 3 of these kind of push down, and the 4th one is sticking up. And in this way, the angle between any 2 hydrogens is 109.5. That's more separation than 90 degrees. This shape is called a tetrahedron. Tetra meaning 4, hedron meaning a shape with sides, right? A cube has 6 sides. A tetrahedron has 4 sides. This is not a shape that we run into very often.
Unless you play Dungeons and Dragons.
I was just going to say that. Unless you play Dungeons and Dragons, there are dice that are shaped like tetrahedrons and octahedrons and all kinds of other hedrons, right? Various sides. So this is a tetrahedral shape, a tetrahedral geometry. And this is what happens every time we have 4 electron groups, because that's how they're going to spread out from each other. Any questions? Let's look at ammonia, NH3. Here's the Lewis structure for NH3. How many electron groups? Not 3. 4. A lone pair is an electron group. So we have the 3 single bonds, and then we have the lone pair. The lone pair is like a bond that's kind of not attached to anything else. That's why it's alone, right? It doesn't join 2 things together, but it's there, and it's repulsive. And actually, it's a little more repulsive to the bonds than other bonds are. So we have 4 electron groups. 4 electron groups make a tetrahedron. But this time, one of the corners isn't an atom, it's that lone pair. The way I think of it is, you could think of this as being balloons, which, if I'd had my head on straight, I would have had balloons today, and we'd be blowing up balloons and tying them together with string, but I forgot. Maybe next time. I think of these like balloons. If you tie 4 balloons together at their necks, they will naturally make a tetrahedral shape, because that's how they get away from each other, because they're bulky and they get in each other's way. So this is like the 4 balloons, they make a tetrahedron, but now one of them is invisible. So the electron geometry, the geometry of the electron groups is still a tetrahedron. But electrons are crazy small, right? So this is the actual shape of the molecule, because the lone pair, there's no atom there. So there's electron geometry and there's molecular geometry. We always have to look at the electron geometry first. When we look at the molecular geometry, you take any lone pairs and pretend that they're invisible and look at what you have left. So we end up with this shape. Well, this is a triangular shape, but it isn't flat anymore, is it? So instead of trigonal planar, this is a trigonal pyramid. You see how the nitrogen in the middle is sticking up a little bit? It's a very shallow pyramid, but it's a pyramid, a triangular pyramid. So the geometry of the electrons is tetrahedral. The molecular geometry is trigonal pyramidal, or a trigonal pyramid. Let's look at water. If you just looked at water and didn't think about it too much, you might think, well, that's linear. That's easy. 2 hydrogens and an oxygen, just like carbon dioxide, right? But when we draw the Lewis structure, there's 2 lone pairs on the central atom. We can't just ignore those. This also has 4 electron groups, right? 2 lone pairs, 2 bonding pairs. So those 4 groups get away from each other by forming a tetrahedron. But this time, 2 of the points are lone pairs, and so we imagine those being invisible, and what we have left is something like this, which has the very fancy name, bent, right? Well, what happened to trigonal pyramidal? That sounds so fancy. No, this is just bent, right? Some of this stuff, it just doesn't make much sense. Anyway, so any questions? It turns out the shapes of the molecules are really, really important when considering many of their chemical and physical properties. Water would not behave the way it does, if it was a linear molecule. How do you like that table? There's a lot of stuff. So you need to know how to predict the shapes of molecules, the molecular geometry, by looking at the formula of a molecule. And we're going to stay to simple ones. We're not going to do complicated ones. We're just going to look at the geometry around one central atom. So you could memorize this whole big table. I don't recommend that. What makes the most sense to me is you think about how many groups are there, and then think about, well, how could that many groups get away from each other? How could they spread out and have as much elbow room as possible? 2 groups are going to go on opposite sides. The electron geometry will be linear. 3 groups make a triangle that's flat, trigonal planar. 4 groups make a tetrahedron. Question?
So it's only like linear, it's just like lone pairs in the middle? Is that like the...
Right. In Chem 3A, we are not going to see any linear molecules that have lone pairs on the central atom. I'm not saying they don't exist, but we're not going there. So those are the 3 electron geometries: linear, trigonal planar, and tetrahedral. From that point, if there are lone pairs, you pretend that those are invisible, and then you name what's left. So that makes a couple more shapes. We've got the trigonal pyramid, and we've got the bent shape. But really, it's not much more than that. So this is, a great table, but I think it often intimidates students. Any questions? I'm going to do some examples. Here's the set of instructions for those of you who like directions. So to predict geometry of a molecule using Vesper theory, first you have to start with a correct Lewis structure. On an exam, for 3A, I like to separate skills as much as I can. So the drawing of the Lewis structure will probably be on one question, and the predicting the shape, I'll give you the Lewis structure and ask you what the shape is. After you do that, you have to look at the total number of electron groups, remembering that a group is a lone pair, a single bond, a double bond, or a triple bond. So you figure out so then we're going to look at the number of bonding groups, and lone pairs. And then your book's directions are just silly. Refer to table 10.1 to determine the electron geometry and molecular geometry. Well, that's great for your homework. I'm not going to give you the table on the exam. So that's not a good idea. That's just stupid. Okay, so what do you do instead? figure out the electron and molecular geometries by determining or considering how the electron groups can get as far away as possible from each other. Okay, so 4 electron groups make a tetrahedron, right? And then you imagine any lone pairs as being invisible, and then name what's left. One thing that might be helpful is playing with a model kit. If you don't have a model kit, which probably none of you do, you can use like gumdrops and toothpicks or marshmallows and toothpicks, and then you can eat them afterwards. But that way you can make a model and see, well, how can I get these things as far away as possible? Use an empty toothpick for a lone pair, and use a toothpick with a gumball on it or a gumdrop on it for the things that are bonded. So let's do some examples. Predict the molecular geometry of ClNO. By the way, some of you are making capital I's instead of lowercase l's. It's really, really important to get your capitalization correct on element symbols. Because for this molecule, if I wrote CINO, that would be a completely different molecule. That would be carbon, iodine, nitrogen, and oxygen. But this is chlorine, nitrogen, and oxygen. So we got to be careful there. So we're told that nitrogen is the central atom. What's the first thing we have to do? We need a Lewis structure. So doing a Lewis structure, we need to figure out how the atoms are arranged. And so we're basically told to put nitrogen in the middle. That means that oxygen is on one side, chlorine on the other. And then we have to figure out how many electrons, valence electrons, do these 3 atoms have together. So we look at chlorine and we find chlorine in the periodic table. It's in group 17 or 7A, and so that means it has 7 valence electrons. So we've got 7 for chlorine. What group is nitrogen in? 5A, or 15, so it has 5. And how many valence electrons does oxygen have? 6. So I think that adds up to 18. So then we're going to put the electrons around. I have to start out with at least a single bond between all my atoms. So there I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. Is that a good Lewis structure? No, we've got somebody without a lone pair. Somebody without an octet. Is it Friday yet? Almost. Okay, so what do? We need to make a multiple bond, right? So to make a multiple bond, I'm going to take a lone pair from this central atom and share it with this chlorine because he's short some electrons here. So I'm going to take that lone pair and share it over here. So now the chlorine has 2, 4, 6, 8. The nitrogen has 2, 4, 6, 8. And the oxygen has 2, 4, 6, 8. So everybody's got 8 valence electrons. Now, some of you might be wondering, well, why does chlorine get the double bond instead of oxygen? That's a topic that's beyond the scope of Chem 3A and actually doesn't matter for this particular question because the question is asking what the molecular geometry is. And regardless of where you put the double bond, the molecular geometry will be the same. So we're not going to worry about it. It would actually be on the oxygen, but it just worked out this way. So here's our Lewis structure. How many electron groups on the central atom? I'm hearing 2, 4, and 3. 3. It is 3. It's 3. 1 double bond is 1 group. 1 lone pair is 1 group. 1 single bond is 1 group. 3. Okay? Everybody okay on that? I know it's kind of confusing. It's not number of electrons. It's not number of electron pairs. it's groups. So we have 3 electron groups. So I'm going to draw a picture here. How would 3 things get away from each other? They're going to make a triangle, right? And this would have a 120-degree angle. Okay, so the electron geometry is trigonal planar. That's the geometry of the electron. Does this picture represent this molecule? No. Because here we have a central atom and 3 atoms bonded to it, and over here there's only 2 atoms. There's a lone pair. So one of these is not an atom, it's a lone pair. Yeah, so the molecular shape of this is bent. Any questions? Let's do another one. Predict the molecular geometry of the sulfite ion, SO3 2-. Well, the sulfur's going to go in the middle, and the oxygens are going to go around it. And we need to know the number of electrons. So the sulfur has 6 valence electrons, and each of the oxygens has 6 valence electrons. And then because of the -2 charge, that means there's 2 extra electrons. Electrons are negative, so I have to add 2. So I've got, what, 26?
Yeah.
Thank you. I love it when people answer my questions. I wish I could get my kids to do that. They just go, okay, so we need bonds, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Cool. We've got enough. We don't need to do any multiple bonds. And then to have a proper Lewis structure, we need to put the brackets, except on mastering chemistry, and put a charge on that of 2-. Okay, so this is where an exam question would start. I'd give you this and say, what's the molecular geometry? How many electron groups on the central atom? 4. 3 single bonds and a lone pair. So then we say, well, how do 4 things get away from each other? Tetrahedral. So we have this one coming out in front and this one going in the back. It's a little tricky. So it's a tetrahedral geometry, but we have a lone pair. So one of these guys is a lone pair. So that's basically invisible, right? So then we look at what's left here. It's triangular, but it's not flat. So this is trigonal, that's the wrong writing tool. Trigonal pyramid. And because the exams are multiple choice, you don't actually need to remember exactly how to spell those things. But you do need to be able to recognize them, right? Well, trigonal pyramid is different than trigonal planar. Questions? Yes. Oh, sorry.
I'm sorry, so is it tetrahedral and
Trigonal pyramid. So the question is it tetrahedral and trigonal pyramid? In a way, the electron geometry is tetrahedral, the geometry of the electrons, but the molecular geometry is trigonal pyramid. So molecular geometry looks at where the actual atoms are, okay? But you can't determine that without looking at the electrons first, because this lone pair of electrons, even though it doesn't show up on the molecule because it's invisible, it's so small, it has an effect on the geometry. If the lone pair wasn't there, then this would be a trigonal planar molecule, and instead of 109.5 degree angles, it would be 120 degree angles. Does that help? Any other questions? So drawing these things, drawing three-dimensional things on a two-dimensional piece of paper or screen can be difficult. So these are the conventions that we use. We use a straight line to indicate a bond that is in the plane of the paper or the screen. A hashed line represents things that are projecting behind the screen or the paper. And the wedged line is projecting out. So a trigonal planar shape might be drawn like this. So I'm going to put those three in the plane of the screen. And this one with a solid wedge is coming out at you, it's coming out. And then back here with the dashed line, like you can't really see it because it's behind the paper, is the one that's in back. Okay, so that's, and you know, there's easier ways and harder ways to draw a molecule. You could draw it from different angles. And so I choose to always draw them like this because that looks the best to me. When they draw something like this, I'm like, that looks like, I don't know, some mess of a thing. I'd rather draw it like this. It looks like it's sitting upright to me. So the major geometries would be linear, trigonal planar, and bent. Notice all of these can be drawn with just regular lines because they can all be two-dimensional. And then we have tetrahedral and trigonal pyramid, which is the tetrahedron that's missing a point. Any questions?